All right. Our next talk is Identicals by Logic from Andrea Salvador. Andrea is a PhD student at the University of Italian Switzerland at Lugano.
Thank you very much. Thank you everybody for being here and to the organizers for the conference. So I will talk about identicals by logic and what do I mean by identicals by logic. So I will start by explaining that. I mean basically sentences that are generalized identicals simply in virtue of their logical form. So I will start by explaining what is generalized identity, what are generalized identical statements. Then I'll go through what are the available proposals for Truthmaker Semantics for generalized identity and related logics, and why I think they are too limited in their scope, and that's what leads me to proposing a new logic and new semantics for generalized identity. In terms of identity makers and difference makers in the abstract, I call them identity states and different states, but I like this nomenclature more. And then I will show that the logic I propose is sound with respect to the semantics. And I'll conclude with some summary and possible future work. So, generalized identity is the notion that we use to say these things. So I've put these examples. You have the justice formulation of generalized identities, or the for plus justice formulation, or the idea also that there is no difference between some things being the case and other thing being the case. For example, the glass being half full and the glass being half empty, they are the same thing, Pace optimists. Or is also the form in which you may give some real definitions. So, for example, you may think that to be a human just is to be a rational animal, and you say that by using a generalized identity. And even though the name generalized identity, the term is recent, was introduced by Lindebaugh, as far as I know, these kinds of statements are statements that have been in philosophy throughout and since the start of it. But they're not only some strange philosophical artifact. As far as I know, they're also found in natural languages. These are two examples that I've found. On the left, you have the window of a store in Amsterdam that I saw a couple of months ago. And on the right, you have what was a picture hanging on a wall in the hotel I'm staying in Munich right now. These identities keep popping up in my life. So I will use this symbol here, the 3 lines symbol, to say that A and B are generalized identical. And these are other glosses that you find in the literature for when two things are generalized identical. Here are also the main features of generalized identity that at least those relevant for my talk. So it is an equivalence relation so to speak. Of course, it's not a relation because that doesn't obtain between things, but at the level of the statements or proposition. So there's no idea of reduction because generalized identity is supposed to be symmetric. And it's also doesn't reduce to synonymy of the components of the sentences. And generalized identities are non-contingently, they are non-contingent in the sense that if they are true, they're necessarily true, and if false, necessarily false. And they also imply necessities in this form. If A is identical to B, then they are the same. So, of course, it's necessary that if A, then B, and vice versa. And also, plausibly, they are about the same thing. So, for example, this rules out the case in which two necessary truths are automatically generalized identical simply because they are true at the same possible words, for example. And also, you can use this idea to argue against absorption laws, because in both absorption laws you introduce another sentence which may be about entirely different things than the sentence you have on the other side. So this is it, and the idea is then what are the identities that are true simply because of their logical form. And since it is a hyperintentional notion, I've decided to use Truthmaker Semantics because it allows you to make hyperintentional distinctions. So it's at least a good way at the beginning to go in this way. So I'm not the only one to have talked about generalized identities. These are the other three approaches that have applied Truthmaker Semantics to generalized identity. One is by Brasmeki, who is here at the conference, so I'm glad about that. And I argue that they are too limited in their scope, as I said earlier. By this, I mean that certain identities that should be valid, you cannot derive them; they aren't valid, and other identities that you may want to be invalid cannot prove that they are invalid. For example, by building a counter model. So the problem is with iterated identities. So let's say that our language is the formulas of our language are defined inductively in this way. So we can, of course, have the usual sentences plus identities between them. And also, in this case, we allow for identities between identities. And we, in this language, have sentences that are Boolean in the sense that they are built only from atoms, or other Boolean sentences using negation, conjunction, and disjunction. So, and an identity is iterated when the sentences A and B are not Boolean. So basically, there is an identity occurring in A or in B. And well, first, let's have a look at the usual approaches in the semantics. You have basically two ways for giving the definition of truth in a model for generalized identity. One is a bilateral approach, which is the approach by Brasmeki and Elgin, for which A is identical to B when they have the same verifiers and falsifiers. And the other is a unilateral approach, so you only consider the identity of the verifiers. Now, they do not provide verifiers and falsifiers directly for GIs, so this definition of truth in a model does not apply to iterated GIs because we cannot identify verifiers and falsifiers of GIs. And also, then logical consequence, which is defined in terms of truth in a model, does not apply to iterated GIs. And in fact, usually, for example, in Brasmeki and Correa's approach, you cannot even form iterated GIs in your language because they would be ill-formed. And these limitations also have limitations in parallel limitations in the logic because, as I said, iterated GIs are ill-formed, and certain valid iterated identities that we will see in a few minutes cannot be derived. And also, certain rules that should be valid for generalized identity cannot be proven to hold in full generality because you do not have a way to treat the cases in which you have iterated identities and the rules that apply to them. And I will therefore introduce a semantics in which you can have instead verifiers and falsifiers directly for generalized identities, so that you can instead have iterated generalized identities that are valid, and also the rules I was mentioning that hold in full generality. So what are these iterated identities that should be valid? Well, given that identity is symmetric, you may want that A is identical to B is the same as saying that B is identical to A, because order there doesn't matter, doesn't seem to matter. But also that if A is identical to B, then identifying A with C and B with C, they are the same thing because there's no difference between A and B. So how can there be a difference between the identity of A and C and the identity of B and C? And on a bilateral approach, you may also want to have that the identity of A and B is the same thing as the identity of not A and not B, given the way we usually understand verifiers and falsifiers of negations. So cannot have them in the approaches by Elgin, Correia, and Brasmaky for the reasons I've said, but also rule of identity elimination, which is some version of modus ponens, we may say, for generalized identity, cannot hold in full generality because you cannot let A be an identity, for otherwise A is identical to B will be informed, and also semantically you wouldn't have a way to treat to show that the rule is sound and valid. And for the same reason, then you cannot have Leibniz's law to hold in full generality. Also, there are other identities that you don't want to be valid. So, for example, the reflexive case in which A is identical to A is identical to another arbitrary B identical to itself. Again, intuitively, these could be sentences that are about different things, so they shouldn't be automatically identical. Or even in the other case of conjunction and disjunction, we know that we can have conjunctions with the same verifiers and falsifiers without having the conjuncts that are pairwise identical. And then there is also this case which may be less clear, that shouldn't be valid. I think it shouldn't, but the idea is that, well, since identity is transitive, then you may, as we said above, we had that A is identical to B, is identical to B, is identical to A. Then in this case, since it is transitive, you may want to have that. I think should not, but for the reason we saw, we will see. And so I don't have time to say why I prefer among the available approaches Brasmaky's one. So we'll just assume it's the right way to go. And thus I will show how one can extend his approach to include treatment of iterated identities and also have a semantics for cases like this, and in which you have verifiers and falsifiers for identities. And the logic I will deal with is given by these axioms and these rules from which you can derive all the axioms rules that Brasmaky has. So let's go to the semantics. So, well, the models are the models are based on modelized state spaces, which are built in the usual way. So I will not go through the details very much. These are the usual requirements that we have. Then I will introduce identity frames. So these are state spaces enriched with two functions. One is the function I, which will give us identity makers, and the function D that will give us difference makers. So we have the domain of I, which is a subset of the set of states, and it assigns to states in that subset an equivalence relation on some sets of states. And instead, for difference makers, that will be a symmetric relation. These are intended to mimic, in a sense, on one hand, identity, and on the other, difference, but they're not the same thing. So, for example, this allows us to have states that identify propositions that are different. This will be plausibly impossible states, but it's something that in Truthmaker Semantics we are fine with, or difference makers that distinguish a certain proposition from itself. And again, this will be a plausibly impossible state. So given this machinery can define what are identity makers and difference makers relative to certain sets of states, and therefore also pairs thereof. So both for unilateral propositions and bilateral propositions. So we may say that S is an identity maker for P and Q when P and Q are an equivalence relation associated to S. And S is a difference maker for P and Q when they are in the symmetric relation assigned to S. So the idea is that S identifies P and Q and S distinguishes P and Q. I mean, the case, and we can then define also the same relation for bilateral propositions. So since they are pairs, for two pairs to be identical, they have to have the same element in the first place and the same element in the second place. So a state will identify two bilateral propositions when it identifies the verifiers of the one with the verifiers of the other, and also the falsifiers of the one and the falsifiers of the others. And instead, for difference, it is enough that one of the elements is different. So it needs to distinguish at least one of the elements. So there are the models I'm going to work with. They are sequences in which we have a modelized state space, then the evaluation functions, and the functions for identity and difference. But I've also added an element which is a set of propositions, which are the pairs of sets of states that the model accepts, so to speak, as propositions. This is, will be useful then to impose a requirement on what are the bilateral propositions expressed by identities. And we will see what that is, but it's not something substantially new from what we already do. So yeah, we have an identity frame, a domain of propositions, which give us a domain of contents, and then evaluation functions, which works in the usual way, but the bilateral proposition assigned to an atom needs to be a proposition. So we then have the inclusive semantic clauses plus clauses for verifiers and falsifiers of generalized identities. And so it's basically what we saw earlier, in a sense, that S is a verifier for the identity of A and B if S identifies the verifiers of A with those of B and the falsifiers of A with those of B. And instead, it falsifies the identity if it distinguishes the verifiers or the falsifiers. Now, we will need to put some constraints on the models to have the correct ones, but I think the constraints are plausible. So where does the semantics takes us? So we have we specify a class of models which are called the class of classical, normal, closed identity models. So the model is classical and closed if the set of propositions of the model is a set of classical propositions, and is closed if it is the set also of closed propositions. So propositions in that set will need to be both classical and closed. And then what is normality for identity models? Well, it's this. It needs to satisfy both coordination and veridicality. So coordination is the requirement that if P and Q are propositions, then also one of these pairs is a proposition, and those will of course be the bilateral propositions that are associated to identities. And then we have, so that we can have, for example, that an atom is assigned the same proposition of a generalized identity. Because otherwise, we don't have that, since the identity and difference functions are primitive. And I also impose this requirement of veridicality. So the idea is that different contents cannot be identified by a possible state, because if that state is possible and instead the propositions, the contents actually are distinct, then that state should not be possible, because it says something about the model that is not realized in that model in a certain sense. And similarly for difference makers. So if the difference maker for P and Q is possible, then P and Q are indeed different. Then coordination allows us to generalize these results of classicality and closure that we usually prove that if they hold for the atoms, then they hold also for the Boolean formulas that we can have, but we do not have a way to prove it also for generalized identities. And so by coordination, we know that it will hold also for generalized identities. And given that the propositions, the sentences that we have in our language will be assigned classical proposition, we can define classical logical consequence in terms of loose verification. And so I will then be able to prove that the logic I presented you earlier is sound with respect to this class of models under the definition of classical logical consequence in terms of loose verification. So, we have loose verification defined in the usual way. A state loosely verifies A if no falsity maker for A is compatible with S, and then we can define loose consequence, loose validity, and classical consequence in a class of models, and validity in that class of models. And there is also this result, which I do not actually use that much in what follows, but I think it's interesting because it shows that if P and Q are identical in the model, then there is at least a possible state which identifies them. And instead, if they are different, there is at least a possible state that distinguishes them. So, in a sense, what is possible according to the identities and differences that are there in the model are also possible because there is a possible identifier or a possible identity maker or a possible difference maker, given if the propositions are identical or distinct. And so there is like this coherence between what are the possible states and what are the differences and identities that the model has between propositions. Then there is this result that we can prove. There is the result of accuracy, which will do most of the work in proving soundness. We have that for every model in that class and every possible state of that model, the state loosely verifies that A is identical to B if and only if A and B actually express the same bilateral proposition in the model. And we have that by veridicality and the exhaustivity of proposition that we required earlier. Basically, suppose take a certain model in the class and a possible state, and suppose it loosely verifies A is identical to B. Then we know that no falsity maker, no state that distinguishes A and B is compatible with S. By exhaustivity, there must be an identity maker that is compatible with S. That will mean that there will be a possible identity maker for A and B in the set of possible states. And so by veridicality, they will be identical. And instead, if we suppose that it doesn't loosely verify, so at least one difference maker is compatible with S, by veridicality, we'll have that propositions are different. And so we have these corollaries that tells us that a certain identity is valid in the class of models if the two sentences express the same bilateral proposition. And this is in line, therefore, with the bilateral approach to generalized identities. So we can see immediately that the axioms are valid in the class of models because we know that these are identities between the proposition expressed by these sentences hold in all the models of the class. And we also have it for the identity of A and B and not A and not B, given the semantic clause for verifiers and falsifiers of identities. And also idempotence hold given closure and coordination, because given coordination, that also applies to generalized identities, and we can substitute generalized identities for A. Then we can also show that identity elimination is valid in the class of models by veridicality and accuracy. The proof is very simple given accuracy. And also we have Leibniz's law for identity, given that the validity of identity introduction, identity elimination, and then these other axioms allows us to prove that if A is identical to B, then not A is identical to not B, and also a rule similar to conjunction introduction, but for disjunction introduction. So for disjunction, and so we can prove every step of the proof by induction on complexity of C. And then so we also have Leibniz's law, given strong Leibniz's law and identity elimination. Then we also have validity of conjunction introduction, because this is used then to prove the generalization of Leibniz's law. Basically, if you assume that a state loosely verifies A is identical to B, by accuracy, A and B will express the same bilateral propositions. And so we also know that the conjunction of A and C and the conjunction of C and B will have the same verifiers, because every verifier of A is also verifier of B, and also the same falsifier. So they express the same bilateral proposition, and therefore also by accuracy, the state loosely verifies the identity between the conjunction. The proof is similar for identity introduction, since A is identical, the proposition expressed by A is identical to that expressed by B if the state loosely verifies them. Then we have that every state identifying A with C will also identify C with B, and also every state differentiating A from C will also differentiate C with B. And so we have also this result. Then we can also build counter models for these sentences. I haven't put the counter models because when I tried the presentation, I didn't have time. Now I think that I will have a lot more time for the discussion. But the idea is that you can build the counter model because you don't have anything that makes sure that if you have a difference maker for A, you have a difference maker for B, or also identity maker for A, you will have an identity maker for B. And also, in the other case, nothing guarantees that a difference maker for A and A prime will be a difference maker for the conjunction of A and B and the conjunction of A prime and B prime. These will be different propositions. Now, instead, about the transitivity case, given idempotence and Leibniz's law, we have that these transitive case entail that if they are valid, if they are derivable, that A is identical to B will be identical. The A is identical to A and A is identical to B. But again, you can have a state differentiating A from itself. That will be an impossible state. And that state may not say anything about whether A is distinct from B. So I'm concluding a bit earlier than I thought, but so the present semantics allows you to generalize what has been already done by dressmaking and basically also Elgin, because Elgin's system is a fragment of dressmakers. And I think you can also avoid the limitations of Correa's approach. Correa does things in a slightly different way, as we saw. He has a unilateral approach, so you will need, for example, to change the semantic clauses for verifiers and falsifiers of identities to adopt then a more unilateral approach in which you identify only the verifiers of A with those of B to have the identity between A and B, and an analogous. You need to make an analogous change for difference makers for A and B, for A is identical to B, sorry. And it does so by having states which are direct verifiers and falsifiers for the identity. Now, there are some other things that need to be done. For example, to prove completeness for this logic. It's not something that I haven't done yet, but I look forward to do it in the future. But also, there is the question of what logic of exact entailment, for example, you get from for generalized identities from these semantics. So I think that what I've presented today will not be enough for a good logic of exact entailment, because the behavior of the functions of identity and difference is constrained by a little bit, and probably you'll need more constraints on those functions to have interesting results for exact entailment. So that one also needs to check what are the good constraints to have that logic, and also then to specify what happens when you fuse identity makers or even falsity makers, or both. That's something that I haven't done already. And there's also a question of how to extend the semantics to deal with the first order logic case. And this was all for today. I hope we can discuss this in the Q&A. Thank you, everybody, for your attention.